Hello everyone, my name is Sandra Haidar. I will be presenting a project titled Design of Power Quality Virtual Lab Toolbox using LabVIEW and Multisim. From that, what is power quality? Power quality is defined as a set of electrical boundaries that allows equipment to function in its intended manner without significant loss of performance or life expectancy. Power quality is a major concern in the electric power industry as its main goal is to free the system from disturbances and obtaining good performance results in the production cycle. All electrical devices in which power electronics and nonlinear loads are integrated are considered sensitive to power quality disturbances such as electric motors, computers, generators, transformers, or household appliances. Thus, quality loss is a main feature that can determine the severity of an economic loss caused by any disturbance in power systems. As power quality problems are arising, the knowledge in power quality became a must for electrical engineers. The Power Quality Virtual Lab will be used by electrical engineers to enhance their knowledge and awareness on power quality disturbances in according to power quality standards. This lab will point up all kinds of distortions and their effects on power quality indices. It presents itself as a feasible, eco-friendly, and accessible learning tool as it doesn't require any equipment or electrical components to use. Also, it doesn't require the usage of high voltages, which will make it an efficient, risk-free, and a fast learning experience. This virtual lab is proposed to be a training tool that will help in learning and executing the concepts of power quality. Electrical engineers will become more familiar with major power quality issues and more aware about the problems tackling power systems and nonlinear devices. This virtual lab is built using NI LabVIEW and Multisim and is composed out of many simulations and experiments, each with its learning objectives. LabVIEW and Multisim are tools that can be used for acquiring, analyzing, displaying, and storing data. Any circuit built using Multisim can be integrated in the Power Quality Virtual Lab to be analyzed in accordance with the power quality indices. As for the power quality disturbances that a system can be subject to, there are short duration voltage disturbances including voltage sag, voltage swell, and interruption, and also waveform distortion including harmonics and unbalance. Therefore, this is a voltage sag. It is a reduction in the RMS voltage for a short time between 0.08 seconds and 0.16 seconds for less than 90% of the nominal RMS voltage, where the voltage had been decreased from 80 volt to 40 volt. The voltage sag can happen during a starting of a large machine such as the motor. Whereas this is a voltage swell. Unlike the voltage sag, the voltage swell is an increase in the RMS voltage for a short time between 0.08 seconds and 0.16 seconds for more than 110% of the nominal RMS voltage, where the voltage had been increased from 80 volt to around 120 volt. The voltage swell can happen due to losing a large load suddenly. As for the interruption, it is a complete loss of voltage for a small period of time between 0.08 seconds and 0.16 seconds. It can be due to control malfunctions and equipment failures. As for the harmonics, they are present in sinusoidal voltages and currents and appear in all frequencies. However, in the industrial field, the frequencies range between 50 to 60 Hz. They are defined in power systems as a sum of sine wave of different frequencies but multiple of the fundamental frequency. Therefore, a signal containing many harmonic components can be decomposed to more than one signal with different frequencies. A sinusoidal signal loses the proper shape of a sine wave when it becomes distorted with harmonics but remains a periodic signal. The appearance of harmonics is due to the high usage of nonlinear devices and nonlinear loads in power system. As you can see, the harmonics happen between 0.06 seconds and 0.15 seconds. The unbalance is also considered as a power quality disturbance that occurs when having different RMS magnitude of the phases or when the phase angle between each consecutive line is not equal, as it is clear here between 0.04 seconds and 0.15 seconds. The main reason of unbalance is adding loads on a particular phase more than the others. Therefore, many power quality indices affected by these power quality issues are tackled, including the RMS, the RMS voltage, the total harmonic distortion, the distortion index, the crest factor, the displacement power factor, and the true power factor. These power quality indices are crucial in representing, quantifying, and comparing complex power quality phenomena. The implementation of these steps in LabVIEW yield to an interface, and the integration of all these individual components allow the formation of a virtual lab able to showcase the effects of the disturbances on the established power quality indices. So now, as we have all this information, the simulations all attached, the equations and formula all plugged in and designed, what would the electrical engineer see? This is exactly what they will see. The Power Quality Virtual Lab interface will pop up in front of the user to start the process experimenting many power quality disturbances. The electrical engineer can create a voltage sag, a voltage swell, harmonics, interruption, unbalance, and also a combination of more than one disturbance. From the first tab, the electrical engineer would set the voltage peak of the sine wave source, the frequency, and the duration of the signal in their corresponding control blocks. The fundamental waveform will appear in the graph. Here, in the next tab, the user will choose whether the desired change is a sag, a swell, or an interruption. Then we'll set the magnitude of the sag or swell in form of percentage and the start and end time in their corresponding places. It is crucial to mention that the electrical engineer should pay attention in choosing the start and end time of the voltage disturbance within the duration of the signal to actually see the desired change. In the next tab, the user has the option to add harmonics to the system by specifying the order and magnitude of each harmonic component and the duration of the distorted signal. As for the unbalance, it can be created in the Unbalance Control tab by either specifying the phase of unbalanced voltages or by setting the peak voltage of each phase and the desired frequency and duration of the signal. This virtual tool allows the user to choose the type of disturbance they want to investigate, or a combination of disturbances of his choice. In addition, they are able to choose the start and end time of each disturbance separately. Once these steps are accomplished and the model starts running, the results will appear in the next two tabs called, respectively, Obtained Graphs and Power Quality Indices. Many simulations and experiments were prepared to help the electrical engineer enhance their knowledge in power quality and become familiar with major power quality issues and indices. The plot results of the voltage and current, along with the measured parameters, will help the user to come out with the right analysis and interpretation on power quality in terms of indices and problems. For example, two types of disturbances at two different times were simulated using the virtual lab toolbox. This figure represents the original waveform where the values of the voltage peak, the frequency, and the duration of the signal were set by the user. This fundamental waveform is free from any disturbance. In the next figure, the push button is set on the sag side. Therefore, a sag voltage of 60% of the nominal voltage tackles the signal between 0.02 seconds and 0.06 seconds. In addition to the sag created, the signal is distorted by three harmonic components of order 3, 5, and 7 with magnitudes of 10 volt, 50 volt, and 75 volt respectively, as shown in this UI screen. These harmonics interfere in the signal between 0.06 seconds and 0.12 seconds. Up to 50 harmonics can appear in a system. However, only 3 harmonics can be added in this virtual tool, as its main purpose is to learn and investigate the basics and measures of power quality. Therefore, the obtained results of the voltage and current signals are shown in this figure, where the plot 1 represents the three-phase voltage source, plot 2 is the single-phase voltage, and plot 3 is the single-phase current. The two disturbances are clearly marked in the first plot. The first rectangle represents a sag voltage that is less than the fundamental voltage. The second rectangle highlights the distorting signal consisting of the fundamental harmonic component along with the three added harmonics. And then, the power quality indices are being measured and analyzed on the implemented system along with the RLC load before any disturbance, during sag, during the harmonic distortion, and after these disturbances. Some of these power quality indices were generated directly through LabVIEW blocks, others were designed using mathematical blocks to perform the right operations. These measures are displayed in the following table to clearly analyze how the parameters are affected by each disturbance. This table indicates that the RMS value is affected by all types of disturbance. When no disturbance occurs, the RMS voltage is almost 70.5 volt. This RMS value decreases in the case of a sag voltage to reach 28.2 volt, and increase in the case of swell voltage or harmonic distortion to reach 95.38 volt. However, THD, TIF, and VT are only affected in the presence of harmonics. Otherwise, they are equal to zero. The harmonic plot in a normal signal only contains the fundamental component, whereas the harmonic plot of a distorted signal shows the fundamental component along with the third, fifth, and seventh order harmonics. In this case, the THD, TIF, and VT will highly increase. The distortion power factor related to the total harmonic distortion is equal to 1 in a signal free of harmonics. Hence, this factor decreases to 0.18 during the presence of harmonic distortion. And while the displacement power factor remains the same even with the presence of harmonics, the true power factor gets smaller as harmonics are added and becomes less than displacement factor. Both TPF and DPF are equal in non-harmonic situations. To sum it up, in their field work, electrical engineers might face a lot of problems while dealing with the power quality. All new technologies related to nonlinear devices and renewable energy sources generate a huge amount of power quality disturbances. This eco-friendly and cost-efficient virtual lab was designed to enhance the knowledge of the electrical engineer on power quality problems, for them to be aware of all the issues and to be able to handle and manage all the situations properly in their future career as electrical engineers with regards to power quality standards and practice guides. Therefore, this tool is considered as a teaching and training tool to be applied in lab activities after teaching, learning, and discussing the power quality generalities and concepts. And a laboratory manual with several experiments was developed to meet the learning objectives related to power quality. And thank you.